Good morning. Thank you for joining Teledyne ISCO's October webinar focusing on optimizing syringe pump performance. Today's webinar will be led by Dale Clay, Teledyne ISCO's Associate Syringe Pump Product Manager. If you have any questions or comments during the webinar, please use the chat function within the platform and all questions will be answered at the end of the presentation. At this time, I will hand it over to Dale.
Hello, my name is Dale Clay, the Syringe Pump Product Associate Manager, and I will be your presenter today. After 39 years at Teledyne ISCO, I'm only one of many experienced, dedicated people here that can help with your product application support from research and development to production. At ISCO, we have a large number of pump models and accessories to choose from in order to solve your pumping problem with great accuracy and reliability. ISCO pumps can pump almost anything. If the pump can be filled with fluid, then it can be delivered. We can pump things such as slurries and paste, liquid solvents, liquefied gases such as CO2, corrosive fluids, heated fluids, and viscous fluids. Today you will learn important fluid properties, pump technology and design features and their effects on flow rates, computers and system setups, fluid characteristics and how it affects pump performance, troubleshooting tips and solutions. Our first topic is fluids. Fluid conditions and properties such as pressure, volume, and temperature, or phases of matter, where the fluid is a gas, a liquid, or a solid, as can be seen in the phase diagram chart on the right. It is important to know the state of the fluid at each point in the fluid system. Vapor pressure, fluid compressibility. While in many applications fluids can be considered incompressible, it can become an important factor with lower flow rates in trying to reach optimum performance. Fluid viscosity is an important property for refilling. Also, it's important to know whether your fluid is an Newtonian or non-Newtonian fluid. Non-Newtonian fluids are affected by the shearing effect of tubing bends with an increase in effective viscosity. Optimizing requires an understanding of the fluid properties and their effect on flow performance. You may have pressure variations, and you can take into account the compressibility factors and then volume, which can provide dampening effects. That is, how a fluid can expand and contract with changes in pressure can affect those changes, how they're affected by volume. Larger volumes will have a larger dampening effect and can smooth out flow rates and pressures. Temperature variations, which expand and contract the fluid, thereby changing the flow rate. And also the effects of refilling from high viscosity fluids, which can create cavitation issues. If the pump can't be properly filled, then the initial flow rates are affected. Our pump is a positive displacement piston pump. It refills fluid at a known volume and dispenses that fluid at the same volume. Our pump is computer controlled of a DC servo motor, which has a single speed gear set. The gear train consists of a motor with an encoder, which controls the speed of the gears, the sets, the worm gear, the ball screw, and the piston. The piston is moved up or down depending on the direction, how the direction the motor turns. Displacement resolution, which is the volume dispensed per motor count, that is, this is the volume displaced by the piston as it moves from tack count to tack count. Pumps with smaller pistons will dispense less fluid per count and thereby have lower displacement numbers, and therefore they have better flow performance. Mechanical errors affect things such as gear imperfections, which can be lessened with smaller pistons. The piston speed can be controlled separately for refill or delivery. The refill, therefore, can be slowed down for viscous fluids. The drawing on the left is a cross-section of the cylinder cap, the cylinder, and the piston assembly. Starting from top to bottom, the cylinder cap with a pressure has a pressure transducer with a seal. The cylinder cap seal located between the cylinder cap and the cylinder is shown in blue. The piston seal, shown in purple, this is the main seal for holding pressure and is a lip seal. The pressure on top of the seal, the pressure on top will force the lips of the seal out, thereby creating the seal. Under the piston seal is a wear ring which supports the seal and prevents wear on the cylinder wall. The lower seal in yellow is the wiper seal, which cleans the cylinder wall from particulates and salts. Also located on the cylinder cap are two ports which are 180 degrees apart, and either can function as an inlet or an outlet. To reduce restrictions from small tubing, there are optional large port sizes for certain pump models. There are a number of things which can cause leaks, and leak sources are placed where fluids can leak outside the pump. The first is the cylinder cap seal, which is a static seal and does not normally need to be replaced, but can leak if the cylinder cap is not tight. The piston seal, again, or the purple seal, is a dynamic seal which moves up and down with the piston and is part of the piston assembly. The seal size and circumference varies with each pump model. Larger pumps have larger seals and therefore could have larger leakage specifications as a result. The cylinder can also cause leaks because of its surface finish. Even though the seal may be in good condition, leakage can occur if the surface finish has become damaged or scratched. This chart shows most of the common pumps with a 1000D on the top row and a 65D on the lower. The 1000D has the largest volume in this chart at 1 liter, and the 65D or the 65DM is the smallest. Pumps are chosen first by the flow rate and pressure. However, for best flow performance, the smallest pump that meets the basic requirements is the best one to choose. You can see that in the last 3 columns. The smaller pumps have the highest accuracy, the lowest leakage rate, and the lowest displacement resolution number. For example, on the 1000D, the flow rate accuracy is plus or minus at 0.5%. The maximum leakage rate is 1.5 microliters a minute, and the displacement resolution is 25.38. This is compared to the 65D, which has a flow rate accuracy of 0.3%, a leakage rate of 0.25, and a displacement resolution of 2.55. Fill efficiency is basically how well a pump fills. Fill efficiency is defined as the volume of pressure, this is when the outlet flow begins, divided by the total volume. For liquids, you would expect something greater than 90%. For liquefied gases, such as CO2, you would expect something around 60 to 80%. The reason for the lower fills with CO2 or liquefied gases is that these gases are much more compressible. Fill efficiency is most commonly affected by higher pump temperatures, especially for CO2 as it can reach the supercritical state, or inlet restrictions or empty supply tanks. A pump technology overview for optimizing requires an understanding of the physical and mechanical effects of flow performance, such as pump model selection, leakage specifications and performance, the piston size, where mechanical variations and has the importance of displacement resolution, the port sizes or tubing sizes and their effects in refilling. Next, we'll talk about the controller and the pumping systems. The controller has many built-in pumping modes. However, we're just going to discuss the 4 below in blue. On the single pump mode, you have the constant flow rate. This is where the flow rate is set, but the pressure will vary. Or constant pressure. This is where the pressure is set, but the flow rate will vary as needed to maintain the pressure even if the pump must back up. Next, we have the multi-pump modes. With 2 pumps put together, you have a continuous constant flow rate. This is the same as a single pump, but the fluid will deliver indefinitely as long as there is fluid supplied to the pump. That is, when one pump is delivering, the other one is refilled, and it will continue to do this indefinitely. Next is the continuous constant pressure system, where the system will operate at a set point of pressure indefinitely. A D-series single pump system consists of a single pump and a controller. A total system consists of, starting from left to right, a refill reservoir or supply tank, an inlet valve that is either manually operated or automated, a syringe pump, an outlet valve, and a user supply device such as a reactor or other device. Then finally at the end, a restrictor such as a back pressure regulator. Also shown in this drawing is a water bath, which can supply as a temperature-controlled fluid to the temperature control jacket installed in a pump. The temperature control jacket is an option in our pumps. We will discuss this a little bit later in the presentation. A D-series continuous flow system consists of two D-series shrimp pump models, a valve package which is either air or electric, and a controller. A continuous flow system consists of, starting from left to right, a reservoir or supply tank on the inlet, then a pump we usually label on the left, which we usually label as pump A, then a valve package which has 4 valves. You have 2 inlets at the bottom, 1 for each pump, and 2 outlets at the top. The 2 inlet valves are connected into a single inlet, and the 2 outlet valves are connected to a single outlet. Pump B is situated on the right of pump A. The outlet then is connected to a user's customer supply device that's not shown in the drawing. A system leak check should be the first thing performed after setting up a system. A summary of the procedure is, first, fill the pump, then close the inlet and outlet valve. Set the pump for constant pressure mode. Select the pressure, then start the pump. After reaching pressure, wait about 15 minutes for the pressure to stabilize. Next, you note the volume remaining on the controller display, and after 30 minutes, note the volume remaining again. Let's note the time difference from the first reading. Finally, then, using this data, you calculate the leakage rate by subtracting the final volume from the first volume and divide by the time as shown in the formula below. For an entire system leak check, the same leak check procedure can be used to determine the leakage rate of any system component, such as the valves, including your user supplied device. To leak check a valve as an example, you dead end the outlet, the valve. In this case, we'll discuss an outlet valve. You dead end the valve with a plug and then open the valve. You follow the same procedure as before with the pump to determine the system leak. That is, pressure and note the initial and final volumes. When you have that information, the component leakage will be the system leakage, that is the pump plus the valve, minus the pump leakage that was previously determined. Next, if you want to do the entire system, you would dead end another component, or you may dead end the customer supplied device, then repeat the procedure. With the data, you would subtract the pump leakage rate that was previously determined, the valve leakage rate, from the total leakage rate, and that will isolate the user supplied device. Next, we'll talk about some troubleshooting solutions. Symptoms such as bubbles in the outlet can be caused by the air not being purged from the system. Note that there is a dead space between the top of the piston and the cylinder cap where the air needs to be purged. You could have inlet line leaks, or the inlet line is not placed down to the reservoir as needed. You could also possibly have cavitation problems caused by low vapor pressure fluids. You could also have a seal leak. Our seals, as we mentioned before, are lip seals. And when you're pulling a vacuum, the lip seals are not designed for pressure coming from behind the seal, and therefore air can leak into the pump. Here are some techniques for resolving the air issue. First is pump the initial flow to waste. That is, pump into a beaker where you can see if any bubbles come up, and pump until the bubbles stop. Another technique is to pre-pressurize the pump first, and then open the valves and flow to waste. And this pre-pressurizing allows the air to be absorbed in the fluid. There is some additional dead space in the seals themselves, and adding some pressure can help the fluids fill these areas and push the air out. So techniques for solving inlet line problems. First, go back through and retighten all the fittings. Ensure your inlet line is placed in the reservoir. And then you can also leak check the inlet line, just like you did before in the previous procedure. But just note that the line needs to be a high pressure line, that is a stainless steel line or Hasselblad line. If it's used as a Teflon line, then the Teflon tubing will not be able to handle the high pressure. So you need to be careful in testing inlet line leaks. Now here's some techniques for problems of cavitation and low pressure fluids or seal leakage. First, you can lower the viscosity by increasing the temperature. Now the pump cylinder piston can be heated up to 100 degrees as standard. But going above this requires a temperature increasing, may require a high temperature package. And with high temperature package, you can go up to possibly up to 200 degrees C. Also, another technique is to increase the reservoir pressure by using a pressure pot. That is by placing your reservoir into a container and pressurizing that container with an air source. Or you could even place a secondary pump on the inlet. Another technique is by placing the reservoir above the pump, as shown in the drawing to the right, and using the gravity as an assist. Here are some symptoms of flow variation, such as room temperature changes, or you might notice some additional fluid loss. Now, the techniques of resolving that, one is to add an insulation around the pump cylinder. Now, the insulation will dampen the effects of temperature changes, say in a room. It will not stop the variation, but it will dampen them. We have insulating covers as an option for most of our pumps, single pumps. For dual pumps, you'll have to wrap some kind of other insulation around. Or also, we have a temperature control jacket. And this is really the best solution. A temperature control jacket will maintain a constant temperature around the cylinder, and then it uses a water bath to maintain that temperature. Now, here are some techniques for cylinder leaks. Now, we've already discussed the typical seals leaking, and the procedure to go through and isolate those leaks. But there may be leaks that are in other places. That is, there may be a leak. You may check the cylinder was at the top in one position, and then may perhaps change the seal as a result of that. And note that if replacing the seals, we do have other seal options. We have virgin Teflon and we have polyethylene. But after changing the seal, you still may have a leak when the piston's in other positions. So to isolate it further, you need to do a leak check at 3 positions. You need to do a leak check at, say, bottom, the top of the cylinder, the middle of the cylinder, and the bottom of the cylinder. If you note that the seal does not leak in one position but leaks in another position, then the problem could be the cylinder itself, and the cylinder needs to be replaced. For symptoms such as poor refills, that could be, again, caused by lower vapor pressure fluids, which can cause gas in the system, or high viscosity fluids, reducing the fluid, amount of fluid getting in the pump, or just simply insufficient fluid. The techniques for this are, one is just to lower the refill rate. That is, give the pump more time to get the fluid into the pump, or add a pressure pot to push the fluid in. Another solution is going to larger tubing or larger valves. We have options for a lot of the pumps for increasing to 1/4 inch or increasing to 3/8, or on a 1000D, we can even go to 1/2 inch. The lower drawing on the left shows a larger port system. You can notice the ports are straight. There's no angle as is in our standard cylinder caps. That further reduces restriction to flow. On the right drawing, indicates a ball valve. And it's showing the ball over here is showing the closed and open position. Notice in the open position, the through hole through the ball valve is the same diameter as the tubing. Thereby, ball valves have the least restriction of most valve types. Now, here's some techniques if you have the problem of insufficient fluids. That is, not enough fluid to fill the pump. First off is you just add a larger reservoir. That would give the more volume. You can pump more fluid longer. Now the last thing is a feature in the pump called a pour fill alarm. Now the pour fill alarm will give an alarm if the fill efficiency drops below a set value. Now to set that up, you can, on the controller, the keypad, you would press menu button, then press A, then 1. Next, you would press a soft key, either A, B, or C, to toggle on or off the fill alarm feature for each pump. Then you can press 1, 2, or 3 to change the fill efficiency anywhere from 10 to 90% for each pump. So as an example, if the fill efficiency is set to 80%, then if the fill is less than 80% of the total volume, then an alarm will sound and let you know there's an issue. Now, for problems in constant pressure mode, with problems such as pressure overshooting the set point or pressure fluctuating around the set point, these two could be important for pressure overshooting. That is, you may have a situation where you do not want the pressure to go above a set point. You set a pressure, say, of 2,000 psi, and you want the pump to come up to 2,000 psi, but you do not want it to go above 2,000 psi. Or the second thing is pressure fluctuating around a set point. We typically use a PID, pressure integral derivative control, for our pressure set points. And there will be a constant oscillating of pressure around that set point. You may want the pump to stop, to reach that pressure point, and then just stop. Now, so the techniques for solving that then is to take the pressure integral and turn it off or on to reduce the overshoot. Or we have then this pressure deadband, which can be turned on or off, which reduces the pressure hunting. That is, in the deadband, you turn it on. Once the pressure is within that range, it's not a single point, but within a range, the pump will stop motion and stop trying to change the pressure to reach a set point. Okay, to change the pressure integral, you're going to press menu, then button A, then A again, and then 5. You'll press the number for each pump module to turn this feature on or off. To set the pressure deadband, you're again going to push menu, then A, then 6. Press the number for each pump module to toggle on or off. Now, I'd like to mention some additional resources. If you're searching for solutions, we have a number of application notes, technical bulletins, all of which can be found at teledyneisco.com. And here's a list of some technical bulletins that may be useful. Much of the information we discussed today are in these technical bulletins. You have metering pump, which is in technical bulletin 15, field verification, temperature control jacket, low flow operation, high temperature, high accuracy technical bulletin 17, diagnostics and troubleshooting in technical bulletin 22. Also, for replacement parts, such as seals, you can visit our online store where you can easily reorder any of your maintenance parts. You go to store.teledyneisco.com. Now we'll pause here for any questions.
Thanks, Dale. Just a reminder, if you have questions, please use the chat function within the platform. We will go ahead and answer them as they come through the chat. And also, I wanted to let everybody know that this webinar is being recorded and it will be shared with all attendees later on this week. So be on the lookout for that email as well. So at this time, Dale will take any questions you may have.